Now let's see the second case, that is input voltage is varying and load resistance RL is fixed. Now we know that when the zener is in the on state only we will have voltage stabilization. When it is in off there is no voltage stabilization. Whatever voltage is variation in the input will pass into the output voltage variations. So when the zener, we have to consider only the states in which the zener is in on state, and there is definitely there is a minimum and maximum value for the input voltage which keeps the zener in the on state. So we are going to get a value or range of values of the input voltage for which the zener is in the state of on, or the voltage which appears across the zener is greater than the zener breakdown voltage Vz. For that we will consider a circuit as shown in the figure. Here I am representing the input voltage Vi, which is a variable one. So we are replacing the cell by a variable cell now. So the input voltage Vi is variable 1 now. Now we want to calculate two conditions, that is what is the minimum value of the Vi, that is what will be the minimum value of the input voltage for which the zener is in the on state. The other condition is that what will be the maximum value of the input voltage which keeps the zener in the on state. So here first of all consider the voltage, minimum voltage. First of all we will consider, or we will have to calculate the minimum input voltage which keeps the zener in the on state. So for that first of all we will do some circuit arrangements, and we assume that V0 is the output voltage which appears across the load resistance. Then to calculate the minimum voltage Vi, that is we denote it by Vi minimum. So when the zener is in on, then the output voltage V0 is definitely equal to the zener breakdown voltage Vz, and is given by V0 is equal to Vi, whatever the voltage, into RL divided by R plus RL. We have seen how we will obtain this expression in the previous discussions. So Vi into RL by R plus RL is the output voltage. Now from this expression we will calculate this Vi, and which is the minimum voltage which keeps the zener in the on state. So that is equal to Vi minimum is equal to, by rearranging the above equation we will get V0 into R plus RL divided by RL. So this is the minimum voltage that will be given to this circuit for keeping the zener in the on state. Now let's see the second case, that is what will be the maximum input voltage that keeps the zener in the on state, that is maximum Vi, we denote it by Vi max. So we want to calculate this value. So for that we will consider the expression for the current, the current flowing through the circuit I is given by IL plus IZ. There is no doubt in it. And we know that when input voltage Vi increases, then I will also increase. The current through the circuit will increase, that is, current drawn from the battery by the circuit will increase, since the resistance, effective resistance of the circuit remains the same. If I increases, you know that if zener is in the breakdown region, then Iz will increase and IL remain constant. So keep this in mind always, that is, when input voltage increases, the current drawn from the battery by the circuit I will increase, and I will increase. This increase in I, the part of since the zener is in the breakdown region, the zener current Iz will increase and IL will remain constant. So if we increase Vi indefinitely, then we can say that Iz will also increase. For every zener diode, there is a maximum value for zener can carry, maximum value for the current the zener can carry, and that is denoted by IZM. The manufacturers of the zener will specify this value IZM, that is, IZM is the maximum value of the zener current that a zener can carry without burning it. So now, when the maximum current, that is I max, is given by IL plus IZM, when the current increases, I increases indefinitely, then Iz will also increase. So there is a maximum current that can be drawn from the battery by the circuit is given by the sum of the load current and the maximum current that zener can carry, that is denoted by Izm. So when Iz become Izm, then I will be the maximum. The corresponding voltage will be the maximum, that is, from the circuit expressions, the previous expressions, we can write Vi will drop across this resistance R, so Vi has to drop across I and R and V0. So from this circuit, or from this node, from the loop 1, by applying Kirchhoff's voltage law, we will get Vi is equal to IR plus the output voltage V0, and Vi maximum will be I max into R plus V0, that is nothing but the zener voltage Vz, and this I max is given by IL plus IZM. So this is the maximum value of the input voltage that keeps the zener in the on state. If we increase the input voltage beyond this value, the current through the zener will reach above the safely handling current of a zener, and the zener will burn out. So the conditions that makes the zener diode in the on state when we are having the variations in the input voltage are Vi minimum is given by Vi minimum is given by R plus RL into V0, that is the zener voltage Vz divided by RL, and Vi maximum, the maximum input voltage that we can apply to the voltage stabilizer circuit, is given by IL plus IZM, that is the maximum current I max into R plus Vz. So from the input voltage should vary between this minimum and maximum values. From this minimum and maximum value, the input voltage should be in between these two values, then only the zener will be in the on state and the circuit can be used for the purpose of voltage stabilization. Thank you.